underlying health conditions. It's not fully known how anyone will react to COVID-19 until they get it. So it's important for everyone to follow health guidance. What precautions are you taking to stay safe?
Now I want to carry on with Unit 2. Unit 2 has got to do with giant covalent structures. It's Unit 10, sorry. Yeah, Unit 10. Let's close up here and see if I've got Unit 10. Okay, Unit 10. It is about giant covalent structures. Now, before we start with this, I want to explain something. Let's just add in a page. All right, people, when we have covalent bonds, the product of a covalent bond is a molecule. Okay, and examples of these molecules are things like water, methane, CO2, NH3. They are, relatively speaking, small molecules. All right, so we just refer to them as molecules. But sometimes a molecule forms a very large structure. Now, we've done a little bit on diamonds and graphite. I said to you, I think, in diamonds, carbon has 4 bonding places. So in diamonds, each of those 4 bonding places are bonded onto 4 carbons. Okay, now, people, we differentiate between, when we have covalent bonds, we differentiate between molecules and macromolecules. The word macro refers to very large. Okay. We basically get 2 types of macromolecules. The one is the giant covalent, and the other one is a so-called polymer. Now, polymers, we won't do much with them at this point. When we do organic chemistry, we will have a look at the polymers. Okay? Maybe when we do a little bit on the chapter on materials, they will refer to the polymers. This module, this Unit 10, has got to do with these giant covalent structures. Okay, and the examples that we are going to have a look at are diamonds, graphite, and silicon dioxide. All right, so people, you have to differentiate between these two. In normal molecules, it's 2 or 3 or 4 or maybe 5 atoms in that molecule. Macromolecules have got thousands sometimes, especially the giant covalent structures of atoms covalently bonded to form a giant covalent structure. Now, normally, what are the properties of molecules? Yes, soft solids, otherwise they are liquids or gases. They have low melting and boiling points, and they are poor or no conductors. Are you with me? These giant covalent molecules, would they have the same properties? Definitely not. Because remember, between these molecules, one water molecule and another water molecule, what forces are there? Very weak forces, van der Waals forces. Alright? But if I have a giant covalent structure like diamonds, where each carbon is bonded onto 4 others and they are bonded covalently onto 4 others, if I want to break that structure, what must I break? I must break the chemical bond. So, we find that macromolecules are usually very hard substances. They have usually got much higher melting and boiling points, and their electrical conductivity will differ, as we will see in the examples that we will do. Alright, so keep that in mind when we work with molecules. Diamonds are molecules, but diamonds are very hard and very strong. They have very high melting and boiling points. Okay, the electrical conductivity differs. Diamonds don't, but graphite does. Okay, so let's have a look. They say giant covalent structures. Remember, giant covalent are macromolecules. Macromolecules can be polymers. Yes, polymers are long chain-like molecules. Your hair is a polymer. The cellulose fiber in the desk is a polymer. Long chain-like molecules. Yes. Okay. So macromolecules, then polymers and giant covalent structures. Alright, so giant structures, very large molecules, thousands of atoms bonded covalently in 3 dimensions. All of them large 3-dimensional structures. The atoms are held together by covalent bonds. So if you want to break them apart, you must break the bond. It will require a lot of energy. And they are joined together to form giant covalent structures. They form part of the group of molecules known as macromolecules. Macro, large. Alright, macromolecules can be divided into 2 types, giant covalent and the polymers. Now, we are looking at the giant covalent. The polymers we'll do later on. Allotropes. What are allotropes? We've done that one. Different crystalline structures for the same element. Normally, if I have an element, it will form a specific crystalline structure, and I can use that structure to identify the substance. Now, some elements have more than one type of crystalline structure. It depends a little bit on the conditions under which they were formed. Diamonds prefer high pressure, high temperature. Graphite is formed under different conditions. So, allotropes, different crystal lattices for the same element. The first allotrope of carbon. The first one, diamonds. The second one, yes, and there is a third one, buckyballs or Buckminster fullerene. Okay. In diamonds, each carbon is bonded onto 4 others. Remember, carbon is actually a very, very unique element because it has 4 bonding places. It's lots of bonding places. Okay? So, to form diamonds, each carbon is bonded covalently onto 4 others, and those 4 are bonded covalently via 4 covalent bonds onto 4 others, forming a giant covalent structure. In diamonds, the carbon atoms are held together by covalent bonds. What do we know about covalent bonds? They are strong, difficult to break, and not intermolecular forces. That's why I can pour water, the molecules can slide over each other, because the forces holding them together are weak. I can't pour diamonds. In actual fact, it's very hard or difficult to break a diamond, because the carbons are held by covalent bonds. The formula for a diamond is just very simply C. C for carbon. Because if you have a big diamond, you'll have more carbon atoms, and if you have a small diamond, you have less carbon atoms. But in diamonds, the carbon atoms are bonded covalently in 3 dimensions onto 4 others, and they in turn onto 4 others. Okay, so there isn't a specific formula. I can't say, like with the Buckminster C60. Are you with me? It's just C because they are, well, C, if you wanted to, you can put a footnote in any natural number, counting number, okay, not naught. Chemical bonds are much stronger than intermolecular forces, so they are difficult to break, and therefore diamonds have high melting and boiling points. In actual fact, diamonds tend to undergo sublimation at very high temperatures. If there is no oxygen available, the carbons will maybe break apart and it will form carbons in the gaseous state. But they very easily condense, and if they condense just under normal atmospheric pressure, it will form soot. The black stuff, if something burns, is carbon. Okay, so diamonds undergo sublimation at very high temperatures, about 3,900. They will melt at extremely high pressures. They will melt. Are the forces between the separate carbons very strong once they've broken apart? No. So they want to actually sublimate and form carbon in the gaseous state. How can I convert a gas to a liquid? By compressing it. Do you understand? That is very hot. And there are diamonds in that fire. They usually react with oxygen in the air and they form carbon dioxide. They burn away. But it has to be very high temperatures. So at very high pressures you will get diamonds to melt. When diamonds are heated in the air, they start reacting with the oxygen and they form carbon dioxide, which is a gas, and it will just dissipate into the air. And you'll have nothing left, yes, of your $15,000 or $25,000 diamond. Now normal fires, it could reach that temperature, but there would probably have to be something that likes burning. A good combustible fuel, yes, something like that. Okay. Now back to the structure. In the structure of diamonds, each carbon has 4 bonding places, and they are filled by means of covalent bonds onto other carbons. There are no free electrons. Why am I interested in the free electrons? Whether it can conduct or not. If there are no free electrons, can it conduct? Nope. So will diamonds conduct? No. All right. So diamonds do not conduct electricity. Where do we use them? Because they are extremely hard. We use them for cutting and drill bits. Very hard points that don't need to be sharpened all that often. It's usually the lower grade. They talk about industrial grade diamonds. What do we do with the other diamonds? Yes, we make jewelry. Why do we make jewelry? Because they tend to have a very high refractive index, so when light shines on them, they sparkle. They do have flaws in them. The pattern is disrupted, and I think sometimes the white diamonds are probably more pure than what a yellow diamond would be, or something like that. Okay, yeah, it's got to do with other substances that also get trapped in that bond. All right, now, graphite. Graphite is the other allotrope of carbon that we have to have a look at. And graphite is actually very interesting because carbon has got 4 bonding places. In graphite, each carbon only bonds onto 3 others. If you look at this carbon over there, it forms 1, 2, 3 bonds. You can take any one. Look at that one, it forms 1, 2, 3 bonds. Look at that one, it forms 1, 2, 3 bonds. Buckminster fullerene forms a ball. So in that way they are similar. But graphite doesn't form a ball. It forms flat sheets having this structure in the 2 sheets together. What would hold this layer onto that layer? What force do we get between molecules? Weak van der Waals forces. That is why graphite is used as a lubricant, because that layer can slide off the next layer. And there are billions of layers in graphite, all right, on molecular level. So we use graphite as a lubricant. All right, so it's flat sheets that can slide off each other. Yes, that's why when you rub it, it's slippery. That's why when you write with your pencil lead, a layer rubs off and is left on your book, and it's just from the force of the friction between your books. Yes. Okay. So, graphite. The molecules are not held together as strongly as in diamonds, because in diamonds, one carbon is bonded covalently onto others. To break a ring-like structure apart is going to require a lot of energy, because there you must break chemical bonds. But to separate one layer from another is very easy, because it's weak van der Waals forces holding the layers together. Okay, so graphite will also have a high melting point, because it's difficult to break covalent bonds. Okay, if you want separate carbon atoms. So a high melting point. It also tends to undergo sublimation. And it will only melt at very high pressures, just like diamonds. You understand? 4,000 Kelvin and 100 atmospheres, 100 times atmospheric pressure. The separate layers of graphite, in other words, that layer and that layer, are held by weak van der Waals forces. So, the layers can slip off each other. They can easily slide off each other. Therefore, graphite, in that sense, is soft and flaky. But the soft and flakiness refers to the layers sliding off. It does not refer to breaking up a layer. All right. Because it's soft and flaky, the layers can slide off. We use graphite as a lubricant, especially in locks, where if you put in oil, the dust goes in and it clogs it eventually again. With graphite, it won't attract the dust, and it will allow the tumblers to slide as they should. Or in a pencil lead. Just go back. Diamonds, a graphite, will they conduct electricity? Yes, because each carbon is bonded onto 3 others. So on each carbon there's 1 electron that's not held in a chemical bond. And that electron is free to carry charge. So that electron will allow graphite to conduct electricity. Do other molecules conduct electricity? No, but remember we're busy with macromolecules. The third macromolecule that we must have a look at is silicon dioxide. Now, I don't have a picture of silicon dioxide. I think in your textbooks there is a picture. If you go and have a look at silicon dioxide, you will see they say silicon exists mainly in the form of silicon dioxide. Look at the formula. It is silicon 4 oxide. Silicon 4 oxide. What does the 4 refer to? Where do we find silicon? Below carbon, how many bonding places? 4. Alright? So, yes, in its simplest form, 2 to 1. So, SiO2 is the formula for silicon dioxide. It's found in quartz and sand. We find that each silicon atom is bonded onto 4 oxygen atoms. Okay? How many bonding places does oxygen have? 2. So each oxygen is going to be bonded onto 2 separate silicons. Do you understand? Yes, it makes it very strong. So we have a large covalent structure molecule. It will have a high melting and boiling point. It will be a very hard solid. Will it conduct electricity? Confuse it over there is silicon itself is a semi-conducting material. So probably, I'm not perfectly sure whether silicon dioxide does conduct or does not. So high melting and boiling point, and if you want to break it, you have to break covalent bonds. So properties of diamonds and silicon dioxide, why do they put them together? How would graphite differ? Graphite is soft and flaky, and graphite will conduct electricity. Okay.
This station subscribes to the Namibia Media Code of Conduct and is regulated by the Media Ombudsman, appointed to deal with complaints about media content that breach this code. This includes content that is inaccurate, unfair, or that invade privacy. We encourage aggrieved members of the public to submit complaints to the Media Ombudsman via mediaombudsmannamibia.org. The Media Ombudsman is supported by the Editors Forum of Namibia, advocating for ethical and quality journalism.
Get uncapped internet from as little as $500 Namibian a month. Contact us now or find us on Facebook. Whitel, your internet service provider.
Last session, we had a look at the different shapes that molecules can have. And we said, just very basically, just to recap, we said that the covalent compounds can be divided up into specific shapes, depending on how many bonding pairs of electrons and how many lone pairs there are on the center atom. We then said that single pair repulsion is the strongest, bonding pair is the weakest. All right. And we found then that molecules can be pushed into specific shapes. Carbon dioxide forms a straight line. We say that molecule is linear. All right. Most of the covalent compounds that consist of two atoms will be linear. Then we said water. Can anyone remember the angle that there was between the hydrogen, oxygen, hydrogen on the water? I think it was 107 or 104.5. Okay, we'll have a look at them in a moment. But we said then the water molecule is V-shaped. Ammonia, NH3, is pyramidal, and methane is tetrahedral. Now we are going to have a look at them as we do in theory. Okay. Now, what is important is that carbon forms the center atom. We have two bonding pairs there, two bonding pairs there, two single pairs, two single pairs. We will find that the repulsion on both sides of the center atom is the same. All right, and it will push the angle between the oxygen, carbon, oxygen into a straight line there. All right. So the repulsion of the oxygen atoms is the same. Therefore, the bond angle is 180 degrees, forming a linear shape. Very important, the name of the shape. Then from that, we can go and have a look at the water. We see here that the oxygen has got two single pairs which repel each other strongly in 3 dimensions as far away as possible. Then we have a bonding pair over here, bonding pair. So the repulsion between bonding pairs and single pairs is also fairly strong, but not as strong as between the single pairs only. So that also pushes the hydrogen atoms away downwards to one side. The repulsion between this bonding pair and that bonding pair is very weak, so they can't repel each other very strongly. And as a result of that, we find that the bond angle over here is going to be 104.5 degrees. Now you need to remember the size of the angle. Okay, they won't ask you obscure examples, but you need to know carbon dioxide, water, ammonia, and methane. All right, it's just basic classical, or the classic examples for V-shaped pyramidal tetrahedral. Okay, so water then is 104.5 degrees, the bond angle. The next molecule that we have to have a look at is the ammonia molecule. Remember, it's NH3. So in the ammonia molecule, we have got 3 bonding pairs that repel each other fairly weakly. All right? So the repulsion over here and over there is not very strong. And, well, over there, remember, it's 3-dimensional. It's not very strong. We only have 1 single pair over here. So we don't have single pair repulsion like we had in water. All right? We've only got single pair, bonding pair repulsion, and bonding pair. That is why we find that the bond angle in the ammonia molecule over there, that angle, is slightly bigger than in water, because the forces pushing those hydrogens down to one side are slightly weaker. So the angle over here is 107 degrees. Same over there as well, 107 degrees. All right. Okay. The last one, we call the shape then of the ammonia molecule, where we have a single atom over here and 3 on the bottom, forming a triangular base. We call that triangular pyramidal or just pyramidal. All right. There we go. Is a pyramidal shape. Then methane is probably the easiest one to explain of the lot. Are there any single pairs of electrons? No. We have 4 sets of bonding pairs. There's one set, there's another set, and another set. And we find now that the repulsion between these pairs are fairly weak, but it is the same in 3 dimensions. There's not a force pushing it stronger from one side of that molecule. So these carbon-hydrogen the hydrogen-carbon-hydrogen angles will all be the same size, and they will be as far away as possible that they can get in 3 dimensions, forming an angle of 109.5. So, try and remember it. Water, 104.5. What was ammonia? 107, and the last one that we've done now, 109.5. So 4, 5, 6, 7, 8, 9. Okay, try and get yourself a system to remember the size of the bond angle. If you can remember the sizes, you would be able to figure out which size belongs to which atom. Why is the bond angle in water smaller than in methane or ammonia? Because in water, we have got single pair repulsion that pushes the hydrogen atoms down. You follow? All right. Why is the angle in ammonia bigger than the angle in methane? Methane only has bonding pairs which repel each other equally weak in all directions, while in the ammonia molecule there is one single pair that repels the bonding pairs fairly strongly away. All right. So you need to try and remember the size of the bond angle. Okay. People, now we've had a look at ionic bonding. We've had a look at covalent bonding. Now we're going to compare the properties of ionic compounds and covalent compounds. Now the physical properties of these compounds have got to do with the strength